Hi, Dr. G here. In this video, we're just going to kind of do a summary, an overview, or a review of composite functions and one-to-one functions. And we'll end by talking briefly about inverse functions, but that'll be a topic of another video. So I just want to review what the definitions are, and we'll do a couple of examples. So a composite function is a new function that we get by composing two old functions. Remember, we've been able to multiply functions to get new functions, add, subtract them to get new functions, divide them, etc. So composition is a new operation on functions. And there's two ways to do it. It's starting with two functions, f of x and g of x. We can compose them in two different ways to get two different new functions. So one way is called f composed with g of x. And the symbol is a little circle. That's not multiplication. We're not multiplying. And the other way to do it is called g composed with f of x. And notice the order is different. And the results will be different too. So in the first one, f composed with g, the definition of that new function is f of g of x. So we're plugging g of x, the output of g, into f as the input of f. In the second one, g composed with f of x is going to be g of f of x. So we plug x into f first, then take the output and plug that into g. So let's look at a quick example. So suppose our f of x is 3x minus 5. So it's a rule that says take your input, multiply it by 3, then subtract 5 from that. Suppose g of x is the function that says x squared minus 2x minus 1. So take your input and square it, then subtract 2 times that input, and then subtract 1 from that. So let's see what happens when we do f composed with g of x. So remember, the definition is f of g of x. So we're going to take f and we're going to plug in that quadratic x squared minus 2x minus 1 as our new input. And so remember f says take that input and multiply it by 3 and then subtract 5 from that. So we can now simplify this, distribute that 3, and now subtract that 5, we'll get 3x squared minus 6x minus 8, a new quadratic function. So let's see what function we get when we do g composed with f of x. We do it in a different order. So the definition of this is g of f of x. So we're going to take g and plug in that linear function 3x minus 5. So remember what the rule for g is, take that input and square it, then subtract 2 times the input, then subtract 1 from that. So we're going to have to simplify this. 3x minus 5 squared, we're using the perfect square trinomial pattern, 9x squared minus 30x plus 25. And then I'm going to distribute the negative 2, so negative 2 times 3x is negative 6x, and negative 2 times negative 5 is positive 10, and then I have minus 1. And now if I combine all my like terms, I get 9x squared minus 36x plus 34. And notice the difference. We really did get two different functions just by composing f and g in different ways, in different orders. So order is very important. So let's review what it means to be one-to-one. A function is one-to-one if every output of the function comes from exactly one input. And remember, a function is just a set of ordered pairs, right? So another way to say this is if we say that every y coordinate appears in only one ordered pair. So every y-coordinate has a unique x-coordinate that goes with it. Now this definition may look similar to the definition of a function, so let's review what that was. To be a function, each x-coordinate appears in only one ordered pair. So when we were concerned with whether a relation or a set of ordered pairs was a function, we were concerned with whether the x-coordinate appeared more than once in the set of ordered pairs. But to be a one-to-one function, we need to be concerned with the y-coordinate as well and see if the y-coordinates all appear in only one ordered pair. Very similar but very different definitions. So let's look at an example. Remember, the graph of a parabola represents a quadratic function. How do we know it's a function? Remember, we had a test. So if we draw a vertical line, remember the equation of a vertical line is something like x equals k. So every point on that vertical line has the same x-coordinate. Well, notice that there's no way I can find a vertical line that will intersect this parabola more than once. So I could move this vertical line around and there's no way I can make it intersect that parabola more than once. So every x-coordinate appears in only one ordered pair on that graph. So that means, yes, this is a function and it passes what we call the vertical line test. So what about one-to-one? Is it a one-to-one function? Well, now we're concerned with the y-coordinate. So if we draw a horizontal line, remember the equation of a horizontal line is y equals some number k. So all the points on that line have the same y-coordinate. Well, notice I just drew a line that intersected the parabola twice. So that means there are 2 points on that graph with the same y-coordinate, but 2 different x-coordinates. One of them has x-coordinate x1 and the other one has x-coordinate x2. So I've got 2 different points with the same y-coordinate. And that's not okay. That's a function, but it's not a one-to-one function. So we just failed what we call the horizontal line test. So in general, all quadratic functions, the graphs are always parabolas, and this will always happen. So in general, quadratic functions, they're functions, but they are not one-to-one functions. They will all fail the horizontal line test, but they'll pass the vertical line test. So what about lines? Are all lines functions? And if so, are they all one-to-one functions? So first of all, a vertical line. So a vertical line, say it has equation x equals k. Well, that means that every point on that vertical line has the same x-coordinate. All different y-coordinates but the same x-coordinate. So that is not a function. Obviously, that fails the vertical line test. It is a vertical line that intersects itself more than once. So a vertical line isn't even a function. But it's a relation, right? It's a set of ordered pairs. And it does happen to be a one-to-one relation, but not a one-to-one function. And we're usually really only concerned with functions that happen to be one-to-one. So what about a horizontal line? So a horizontal line has equation y equals k. So all the points will have the same y-coordinate, but they'll all have different x-coordinates. So a horizontal line is a function. It will pass the vertical line test, but it obviously will fail the horizontal line test. So it's not one-to-one. So a horizontal line is a function, but not a one-to-one function. A vertical line isn't a function, but it is a one-to-one relation. So what about non-vertical, non-horizontal lines? Well, those are all functions because they're always going to pass the vertical line test because they're not vertical. So no vertical line will intersect it more than once. And because they're not horizontal, they'll pass the horizontal line test as well. So they're going to be one-to-one. So any line that's non-vertical and non-horizontal is a one-to-one function. All right. Let's look at a picture. Suppose I have a function f of x equals 3x minus 5. There's the domain, a bunch of little points. And one of them is the number 2. And we take f of all these numbers in the domain, and we land in the range of the function f of x. So we get a bunch of little numbers. And in particular, the number 2 goes to 1, because f of 2 is 3 times 2 minus 5, which is 1. All right, so what if then we apply the function g of x to that? And g of x, remember, was x squared minus 2x minus 1. We land in some other set and have some numbers. In particular, the number 1 got sent to 1 squared minus 2 times 1 minus 1, which ends up to be negative 2. So what we just did was we composed f of x and g of x, but in which order? So the function that takes the number 2 to the number negative 2, was that f composed with g, or was that g composed with f? We definitely used both f and g, but in which order did we do them? So what we did was we took f of 2 first, and we got 1, right? Then we applied g to that. So g of f of 2 turned out to be g of 1, which was negative 2. So look at that order. So that's g of f of 2. So that's g composed with f. So it was not f composed with g. Okay, so the order is important, and you may want to use a picture to kind of visualize what's going on. And remember that g composed with f, we actually figured out what that function was. It was 9x squared minus 36x plus 34, right? So let's just check. G composed with f of the number 2 is 9 times 2 squared minus 36 times 2 plus 34, and that's 36 minus 72 plus 34, which is negative 2. Okay, so we checked our work, we verified. All right, so now what about one-to-one functions? So what do those sort of look like when we draw a picture of a function? So it turns out that a one-to-one function has an inverse, and we don't know, I haven't specified the definition of that yet. The definition is in another video. It has an inverse, which turns out to also be a function, not simply a relation. So a function is a set of ordered pairs with a specific property, right? Well, an inverse is also a set of ordered pairs, and it can have that property that makes it also a function. If the first function was a set of ordered pairs that were one-to-one, then the inverse will be also a function. Let's see why that is. So let's draw a picture of a function f. So in this picture, each dot on the left in the domain has exactly one arrow going out of it, and each dot on the right has exactly one arrow coming into it. So because each x-coordinate, each input on the left, has exactly one arrow coming out of it, that makes it a function. And because each dot on the right has exactly one arrow coming into it, that makes it a one-to-one function. So it is both a function and a one-to-one function. To tell if it's a function, you look at the arrows coming out of the dots on the left, the inputs, to see if there's only one arrow coming out of each input. That makes it a function. To make it one-to-one, you look at the outputs on the right. Each output has only one arrow coming into it, so it only came from one input. Each dot only came from one input. So that means it's a one-to-one relation. So a one-to-one function. So if we want to look at the inverse is another relation that just reverses all the arrows. So if I reverse all the arrows, I get a new relation where the inputs are on the left now and the outputs are over on the right. So looking at the inputs only, each input has only one green arrow coming out of it. So we can tell that is a function. And the reason it's a function is because the original function f was one-to-one. Each of those outputs had only one red arrow coming into them. That allows it so that if we use them as inputs, there's only going to be one green arrow coming out. So let's look at a different picture where that doesn't happen. So suppose I have this function f. Each red arrow coming out of the coming out of the blue dots on the left, right? Each blue dot has only one red arrow coming out of it. So f is definitely a function, right? But now look at the blue dots on the right, the outputs. There's one dot that has two arrows hitting it. So that means that f, even though it's a function, it is not a one-to-one function, because one of the outputs has two inputs that hit it. So then if we want to look at the inverse, let's reverse all the arrows with green arrows. So the first one, the green arrow, there's only one green arrow that comes out of that dot. But the second dot has two green arrows leaving it. Okay? So there's an input on the right that has two outputs associated with it on the left, because it has two arrows coming out of it. So that means that f inverse is not a function. It's not even a function. Okay? And that's because the reason it's not a function is because f was not one-to-one. Okay? F was not one-to-one means that if you reverse the arrows, you're not even going to have a function. So that's why one-to-one functions are so important. We often want to reverse them and go backwards and still have a function when we do that. So we need to have f, the original function, we need to have it be one-to-one so that we can reverse it and still have a function. All right, so watch for another video that is specifically about inverse functions. Happy studying.